Scott Jackson. Scott's a extension professor in the Department of Environmental Conservation at UMass in Amherst. He's an expert in wetland ecology, biodiversity conservation, and general New England natural history. And he says he doesn't like long introductions. But we have a surprise for him, because tonight, before he helps us understand what we can do to push back against climate change in our communities, we're taking this opportunity to present Scott with our Conservation Champion of the Year Award. Those of us living and working in the Housatonic watershed are fortunate to have Scott Jackson's expertise helping guide our conservation work over the past 12 years. Scott's landscape ecology research and the assessment and decision-making tools he and his colleagues have developed to put the research into practice have transformed the way we approach land and water protection. He has also all the conservation practitioners using his work to make a difference on the ground. So it's with great gratitude that we honor Scott with HVA's 2022 Conservation Champion Award. Please join me in welcoming Scott as our featured guest.
Thank you very much. I am indeed surprised and delighted. And I want to thank you for inviting me to your party and to the celebration of all that you've accomplished over the past year and over the years before. Congratulations, Lou and Elaine. I'm happy to share a little bit of this moment with you. All of your lifetime work has been very inspiring to listen to the description of all that you've done and all that you've accomplished. And I thank you all very much for acknowledging the work that I did. And I'll just say that I'm really the public face of work that's done by a number of people. I have colleagues at UMass that work down in the dungeon, sort of keeping the wheels turning on this stuff, and they don't nearly get as much of the credit as I do. But on their behalf, I accept your honor and thank you so much for it.
You're very welcome.
So this evening, I've been invited to speak to you about climate adaptation, otherwise known as coping with climate change, and to talk a little bit about what might be done at a community level or even at a personal level to try to safeguard the ecosystems and species and the biodiversity that we value in the face of climate change. My focus is as an ecologist, and so even though I do have some sympathy for the loss of infrastructure, the loss of the damage that's done by flooding and all of that, and I recognize the importance of addressing that, I feel like often the threat of climate change to ecosystems and species sort of has a back seat, and I want to just sort of bring it up to the fore a little bit and talk a bit about how we can focus on the specific climate-related threats that are important to consider as we do our conservation going forward. So I'm going to present some slides where I'm going to talk a little bit about climate change and what kind of changes that might cause for us in New England, and then talk a little bit about climate adaptation in terms of resistance, resilience, and transformation activities that can try to maintain the wildlife and biodiversity of our region. All right, so I'm going to share my screen with you. All right, so just starting with the basics, what we're dealing with here is a recognition over the years that the atmosphere that protects our Earth and makes it possible to support life does so by acting a bit like a greenhouse. And the atmosphere allows some of the energy of the sun to pass through it to warm the Earth. And then as that radiation reflects off the Earth, some of it is retained within by our atmosphere, and other components are radiated out into space. So that's the greenhouse effect, and that's what causes global warming. In global warming, as we look at sort of the average over the last, 200 or 140 years, that line across is the average over 140 years. And you can see that the most recent years, we've been well above the average, and that this is a trend. Now, some people don't want to believe that it's happening. And so every time we get an exceptionally cold spell in the wintertime, you get people starting to doubt whether really climate change is happening, whether global warming is real. And we even had one of our senators get up and officially announce that he found a snowball in Washington, D.C. Therefore, climate change must be a hoax. And so this is, I think, dates back to 2014, if I remember right, when the polar vortex became a term that we suddenly heard about for the first time. At least for me, it was the first time I'd ever heard of such a thing. And it had to do with a particular weather trend that forced polar cold air down into the midsection of North America. And we ended up with exceptionally cold temperatures for a good chunk of the winter. And so if we look at the temperature pattern for that period, so this is January of 2014, you can see that much of Eastern North America was very, very cold and much below average for that, for wintertime. And so were parts of Russia and up in Siberia. But it's also important to note that Greenland and Alaska were the opposite. They had exceptionally warm winters. And that when we talk about global warming, we're talking about what's happening on an average around the globe. And it's been true that every year it gets warmer and warmer on a global basis, even if certain parts of the globe can have particularly cold winters. One of the problems with trying to convince people or keep them convinced that climate change is real is that weather is different than climate, and weather is highly variable. And so when we want to try to figure out trends in a really noisy data set, one of the things that we do is sometimes use what's called rolling averages. And so if we, instead of looking at annual variability, which is the top line on this graph, if we look at a 10-year rolling average, you can see it begins to smooth out a little bit and you start to see a trend. Looking at a 30-year average, it smooths out even further. And with a 60-year average, you can see a very distinct trend in what's happening over time. And so recognizing that some of you may be going to family gatherings over the holidays and mixing up with relatives who may or may not share your views about this issue, I'd like to recommend a little video clip to help explain the difference between weather and climate and help people understand how global warming can be real when it's really cold outside. So I'm going to switch right now to a YouTube video of Neil deGrasse Tyson explaining it in 2 minutes. Now, the video part might be glitchy, but I've been told that the audio is pretty clear. So if it's glitchy, I apologize, but it's a really excellent explanation. So hang on for a minute. All right, and here we go.
Okay, so if we scientists are so good at making these dire long-term predictions about the climate, how come we're so lousy about predicting the weather? Besides, this year, we had a colder winter in my town. For all the scientists know, we could be in for global cooling. Here's the difference between weather and climate. Weather is what the atmosphere does in the short term, hour to hour, day to day. Weather is chaotic, which means that even a microscopic disturbance can lead to large-scale changes. That's why those 10-day weather forecasts are useless. A butterfly flaps its wings in Bali, and 6 weeks later, your outdoor wedding in Maine is ruined. Climate is the long-term average of the weather over a number of years. It's shaped by global forces that alter the energy balance in the atmosphere, such as changes in the sun, tilt of the Earth's axis, the amount of sunlight the Earth reflects back to space, and the concentration of greenhouse gases in the air. A change in any of them affects the climate in ways that are broadly predictable. My friend's meandering represents the short-term fluctuations. That's weather. So almost impossible to predict what will attract his interest next. But not hard to know what the range of his meandering will be, because I'm holding him on a leash. We can't observe climate directly. All we see is the weather. The average weather over the course of years reveals a pattern. I represent that long-term trend, which is climate. Keep your eye on the man, not the dog. Weather is hard to predict, like my friend here, but climate is predictable. Climate has changed many times in the long history of the Earth, but always in response to a global force. The strongest force driving climate change right now is the increasing CO2 from the burning of fossil fuels, which is trapping more heat from the sun. All that additional energy has to go somewhere. Some of it warms the air. Most of it ends up in the oceans. All over the world, the oceans are getting warmer.
This weird new tool is
I hope you enjoyed it. I hope you were able to see some of the video that goes along with it. If you want to see it for yourself or want to share it with one of your relatives over a dinner, all you have to do is go to Google and put in Neil deGrasse Tyson, dog and climate, and you'll find it right away. All right. So the climate at the globe is warming, and when we look for reasons for it, you see a very strong correlation between the warming of the Earth and CO2 concentrations. And as we work to try to tease out how much of that is natural versus how much of it is caused by people, it's now overwhelmingly clear that it's basically human activity that's causing the rise in CO2 and other greenhouse gases like methane, and therefore we are responsible for this global warming. And it's not hypothetical. It's not something that's going to happen. It's going to continue to happen because it's already started. So if we look at the number of frost-free days in the winter season, you can see that it's already changed in our part of the world by 10 days. So we have 10 days more frost-free winter than we used to. If we look at precipitation, the teal areas are additional precipitation above long-term average. And the more intense the color, the more it departs from that average. So in the Northeast, it's getting wetter. In addition to getting wetter, we're also getting more severe storms. And so when you look at the change in very heavy precipitation events, it's increased in our part of the world by 71%. So we are in fact getting more heavy storms, and they're heavier than they used to be. The top line on this graph is the CO2 as it has changed over the last couple of decades. And you can see that it tracks really well with the next line below it, which is the amount of CO2 in the ocean. And when you dissolve CO2 in water, it creates carbonic acid, and carbonic acid is what's making the oceans more acidic. It's changing the ecology of the oceans as the pH goes down over time. The sea level is rising and has been rising for a while and will continue to rise for three principal reasons. One, the warmer the water is, the more space it takes up. It expands as it heats. Two, you have the melting of glaciers and ice caps. And three, the ice cap on the South Pole is so big and so massive that it actually exerts gravitational pull on the waters of the oceans. And most of the water in the oceans is sort of pulled towards the South Pole by that gravity. And once that ice melts, it's going to release that water and it's going to slosh back up to the north. And so in the Northern Hemisphere, we're expecting some significant increases in sea level over the next few decades and centuries. So what can we expect here in New England? Well, our best projections suggest that we're going to continue to see warming temperatures both in the summer and in the winter. And so far, it looks like winter temperatures are going to warm more rapidly than the summer ones. We'll have longer growing seasons. We're going to likely to get more rain in the winter and in the spring, and less rain in the summer and fall, which is really sort of the opposite of what we need, because in the winter, everything is frozen and that water's just going to run off the land and exacerbate flooding problems. In the summer and fall, we're going to be dealing with drought and potential for droughts to get worse over time. We're probably going to get less snow, and snow acts like a blanket in our forested landscapes, and it prevents the frost from going really deep. If you have less snow, you're likely to get deeper frosts. If you get deeper frosts, you may change the germination rates for seeds or the micro biomes in the soil. And it's hard to know exactly how that's going to manifest itself, but it's something worth looking out for. We're going to continue to have more frequent severe storms. We're going to have storms that are of greater severity than we're used to. And a sea level rise on a conservative way is probably going to be 3 to 6 feet or more. These are projections that were done at UMass and are available on a state website that I'll show you at the end of the presentation. But it shows the historical pattern for summer temperatures and winter temperatures, and the projections for where we expect those to go over the next 80 years or so. And what's really sobering about it is if you look at the winter temperature and you see this red line here, this is basically showing us the warmest temperatures that we get in the winter now and for the past time. But when we project forward, that what was warmest now is going to be the coolest winters that they're going to have by 2100. And in the summer, the same thing. What we consider a hot summer now is going to be a cool summer back in 2100. As a result, seasons are changing. Winter is getting shorter. It starts later. It ends earlier. You get longer growing seasons, and changing seasons are already manifesting themselves in terms of when you get leaf out. So bud break for leaves happens a few days earlier than historically, and the blossoming rates for flowers is also earlier than it used to be. This can have really important effects on wildlife in that when the bud breaks happens in the springtime, that generally releases a bunch of invertebrates that will then eat those tender leaves. So you get sort of an explosion of invertebrate life as they feed on these fresh leaves coming out of the buds. It's timed perfectly for when migrant birds are moving through the area and feeding on those insects. And by feeding on the insects, they ensure that not too much damage is done to these young tender leaves and that we get fully leafed out trees. The migration period for the birds seems to be fixed. And so when they're down in South and Central America overwintering, they have no idea what kind of winter we're having or whether we're going to have an early spring or not. So they come through pretty much the same time every year. But if the bud breaks come earlier and earlier and the insects come earlier, then there could be an asynchrony between the bird migration and their need for food and the abundance of insects that they normally depend on. Another example of how changing seasons can affect wildlife, here are 2 species that we have here in New England that typically are brown in the winter and turn white, brown in the summer and turn white in the winter. So the snowshoe hare on the left and the short-tailed weasel or ermine on the right. And so they're, at least with the snowshoe hare, it seems to be genetically fixed, that they turn color at the same time every year, regardless of whether there's snow or not. And because they rely on camouflage to protect themselves from predators, they generally will just sit tight if a predator comes around rather than run for cover. And if they're sitting tight, thinking that they're blending in with a background like this, it's not going to work very well. And so people who study snowshoe hares at this time of year sometimes refer to them as light bulbs because they are so obvious in the landscape that you can actually walk right up to them and drop a net over them because they think they're well hidden, because that's instinctively what they do. So what are we going to do about climate change? Well, there's 2 general approaches that both have to be done at the same time. One is we need to figure out how to mitigate climate change. How can we reduce global warming and largely by reducing greenhouse gas emissions? The other thing that we need to do is adapt. We need to figure out how to try to cope with the global warming and the climate change and try to preserve as much of our wildlife and biodiversity as possible. In terms of mitigation, we're fortunate to live in a state that takes this issue very seriously. And recently, this publication was released, the Massachusetts 2050 Decarbonization Roadmap, which sets forth a strategy for trying to become greenhouse gas neutral in Massachusetts, basically net zero greenhouse gases. And I really encourage you to read this document if you have time, and some of the supporting documents, because it's fascinating reading and it's ambitious, it's integrated, it's comprehensive, and it's an incredible challenge for us to try to implement to achieve our goals. One way that we can try to mitigate climate change is by protecting forests, because forests absorb a lot of carbon. And they also represent long-term storage of carbon that was absorbed in years past. And so one of the strategies in that decarbonization roadmap is to protect as much forest land and wetlands as possible because of the carbon that they already store and their capability of storing more over time. Now, turning to climate change adaptation, which is the main topic of this talk. What do we mean by climate change adaptation? Well, generally it just means getting used to the fact that things are going to be different. Sometimes we can manage that change to try to preserve what we care for, such as let's try not to let the rivers eat our roads. But in other cases, it means becoming resilient so that we can actually recover easily from some kind of disturbance that might be caused by climate change. And in other cases, we may have to just try to guide the change that we can't prevent. Often when we talk about this, like we need resilient roads, we use the word resilient and resiliency as a catch-all for all climate change adaptation. But actually, people who are sort of steeped in this and are trying to come up with strategies and actions break up climate change adaptation into three different categories. So the first is what we call resistance, and that's where we want to avoid climate-related impacts. And so if you are a highway department and you have a road running along the river, you don't want resilience, you want resistance. You want to avoid that road from being washed out. So an example of this might be increasing the water storage potential in upper portions of a watershed so that we can avoid devastating floods or damaging droughts. The second approach is called resiliency, and that's really to enhance our ability to recover from climate-related impacts. And so when we talk about a highway network, resiliency is that if a road gets washed out, there are other roads you can use to get where you need to go. So you can still get to the hospital and you're not reliant on any single road in order to do that. In ecology, resiliency can be expressed as something like increasing tree age and species diversity in the forest to promote more rapid recovery from fire or storm damage or insect damage. And so that's an example of resiliency that we can implement. The third is transition, or in some cases, people call it transformation, which is when you can't resist that change, can you guide it to an acceptable future condition? And an example of this is what the Nature Conservancy calls conserving nature's stage, which is don't focus too much on trying to keep ecosystems fixed where they are. We have no idea what the future is going to hold, especially if we look out a couple of 100 years from now. But we can predict that those areas that have the greatest abiotic diversity, the greatest landscape diversity, are likely to support the greatest diversity of species and protect the greatest amount of biodiversity. Another strategy in this category is assisted migration, which is actively moving plants and animals around because climate change may actually happen faster than these things can disperse naturally. So let's start talking about forests. What are some of the impacts that we expect to have to deal with our forests? Well, higher CO2 levels could increase growth. And the longer growing season could also increase growth in the forests. On the other hand, heat stress, either in the summer or the winter, could decrease forest growth. And certainly drought is going to decrease the amount of growth, and it could increase the mortality in the forests as well. Drought stress can also increase vulnerability to fire. And climate change can result in a change in tree species composition, meaning that maybe we have a hard time holding on to northern hardwood forests, and over time they will transition to transitional hardwoods. I already talked about depth of the frost line and how that might be affected by the reduction in snow cover. Are we also likely to get increased damage due to extreme weather events and ice storms? Because unfortunately our winters become more icy than they are snowy as we get deeper into climate change. And we could expect increased threats from pests and diseases that for now are being kept out of the Northeast by our cold temperatures, but as those temperatures warm, more and more of those southern species are likely to move into our area. So we expect things to change. So this is a map showing the suitability of the habitat for sugar maples in the Northeast or in eastern United States. This is what it's projected to look like in the future. So a lot less sugar maple, a lot less maple syrup. This is the distribution for eastern hemlock. This is what they predict it will be in the future with climate change. This is a bird that likes to nest in eastern hemlock groves. This is the black-throated green warbler, and you can see what its current distribution is, or habitat suitability, and what it's likely to be in the future. So these are the kinds of changes that sometimes we can try to resist, but ultimately we also are going to have to learn to live with. One concept to think about is that perhaps not everywhere is going to change rapidly, and in some places conditions might stay suitable for some of these species, even in the southern portions of their range. It's a concept we call refugia, which are areas that remain relatively buffered from contemporary climate change over time and can enable the persistence of wildlife species or ecosystems in pockets. And if we can connect those pockets together, we might be able to actually conserve those species within our area. Here's a map, a little bit confusing, but important because it's showing temperature related to the hemlock woolly adelgid, which is one of the biggest threats to eastern hemlock in our region. And the area in gray are areas where the current minimum temperature is below 28.8 degrees Celsius. And that's what it is now. But if we project forward in time, the orange is going to represent those areas that fall below that temperature threshold. And why is that temperature threshold important? Well, because sudden declines in temperature following periods of warm temperature causes high mortality in the woolly adelgid. And so in these bands that are gray now and going to be orange in the future, these are the areas that the adelgid is not having the level of destruction that it is having in areas further south. The cold temperatures are controlling the distribution of the adelgid and the damage that it can do. But if you look on the map, you can see that even in Massachusetts and even in the Housatonic watershed in Connecticut, you have pockets that are likely to stay cold enough to resist the adelgid. These may become refugia areas for the eastern hemlock, where they can persist even in other areas where areas around them are, the hemlock is disappearing. So another forest type that we're concerned about is northern hardwoods. And northern hardwoods are sugar maple, paper birch, basswood, beech. And these are important areas, obviously for maple sugaring, but they also have different understory plants. They have different invertebrates that live in them. So what kind of strategies can we have for protecting northern hardwood forests? Well, if we think about resistance, we can look and try to predict northern forest refugia, where they're likely to persist over time, and protect those areas and try to connect them together with other forests in between. Where we have northern forest species on the land, we might want to manage that land carefully to maintain that species composition. So if you have northern forest species in the understory, you could probably open up the canopy and release those younger plants to form a new generation of northern hardwood forest in the mature forest stage. But if the understory is full of other species farther, from farther south, then you may want to be careful not to open the canopy too early, or you are going to speed up the transition of northern hardwoods to other forest types. We want to try to reduce drought and fire risk in any way that we can. And probably foresters will have some ideas on exactly how to do this. I can't really tell you, but if there are ways to do it, that's something to be considered. We need to try to reduce risk from invasive species and diseases. We want to minimize drought and invasive species impacts on overstory trees in particular. So if we can maintain the health of the really healthy trees that maintain most of the canopy, then we can avoid a situation where you're having big breaks in the canopy due to either fire or diseases or drought. And we can maybe on individual parcels reduce the risk of damage from ice loading. And sometimes that has to do with the shape of the junctures in the trees. So U-shaped junctures are more resistant to breaking than V-shaped junctures. And so what trees you use to thin, what trees you maintain might affect the ability to resist ice storms in the future. And where you have trees that have already gone through maybe an infestation or a drought and have survived, you want to keep those trees because they probably are going to survive the next stressful period as well. Resistance and now resilience. Increased forest heterogeneity, to forest diversity, species diversity, age and size diversity, the diversity of environmental conditions that are going to support a diversity of plant life. Where you have particular signature species like hemlock, pitch pine, Atlantic white cedar, tend to pay particular attention to trying to retain those species. You want to try to emulate the range of natural canopy gap sizes so that you can introduce heterogeneity and increase the recruitment environment for different plant species. And also provide opportunities for future adaptive native species that are going to maybe fill in those gaps where other species start to fade away. And in transition, there's something called assisted migration, and there are multiple different elements to it. It could be assisted population expansion, like pignut hickory with southern species that's already present, but we might benefit from expanding their abundance as a mass-producing tree. Assisted range expansion, tulip poplar, we're at the edge of the range for tulip poplar. So we could potentially, by managing carefully in the forest, help spread that tree, which is a very majestic tree, very fast-growing, large and valuable tree. Assisted species migration, where you have species like bloodroot, which is dispersed by ants. It's pretty hard to imagine how far bloodroot's going to expand in response to climate change. It might need some help. Thinking about species substitutions, hemlock is very important for maintaining cold water streams because of the shade that it provides in hemlock ravines. But if hemlock succumbs to the woolly adelgid, is there an opportunity to perhaps use something else, maybe something not even native, but not invasive, that could be planted in those ravines in order to maintain our cold water streams? And then also maintaining trees at the edge of their range as a seed source for potential future expansion. Some of these are controversial. Some of these are still hotly debated amongst conservationists, but all of them are possible options that we might have to consider in the future. Another area that's a focus for your organization is cold, clean, and connected. So cold water streams are going to be stressed with climate change and the species that live in them, from brook trout to spring salamanders. So what can we do about that? Well, again, cold water refugia. There are some streams that are likely to maintain their cold temperatures because of the input of groundwater. Can we identify those areas and protect them and protect the land around them to try to keep them cold? Can we restore riparian forests to maintain cool temperatures in these streams and maybe make them even cooler by restoring areas that are now open land into more forested riparian buffers? We want to disconnect stormwater where we get a twofer. We can actually avoid warm water running into these streams and giving it a thermal shock. And we also can keep them cleaner from avoiding all the runoff from those hot parking lots. Dam removal allows us to control both temperature and connectivity. It maintains connectivity by taking out barriers to movement, but it also prevents the warming of water in the impoundment above dams. And culvert replacement is a way of trying to keep cold waters connected. So dam removals, we're doing a good job in Massachusetts, but there are a heck of a lot of them still out there. Some of them small, some of them larger, but we just got to increase the pace at which we're taking them out. In terms of culverts, I want to sort of illustrate this, thinking about brook trout as an example, where here's a tributary system with favorable cold water habitat for brook trout. With global warming, we might see a reduction in some of that favorable habitat, and we might have the cold water segments confined to tributaries. And so these are a little bit smaller, a little bit more isolated from each other. But at different times of the year, brook trout will still move through the main stem, and they can still keep these areas connected together so that you have gene flow, so that you have supplementation where successful source populations can help maintain sink populations nearby. And when you have bad periods of time, either drought or really hot summers, you may lose some of that cold water habitat temporarily, and you may lose populations of brook trout. But if you have connectivity amongst these different tributaries, then you have a mechanism for recolonizing these tributary habitats and then reestablishing populations so that you don't actually lose them throughout that river system. But if you've got roads that are running through your watersheds, and if you have culverts that are not passable for brook trout, then when you have these losses of populations, you basically short-circuited your ability to recolonize those areas and maintain populations in those tributaries. So there's a lot of work to be done replacing our legacy culverts that were designed only to pass water into the kind of stream simulation culverts that will pass a variety of aquatic organisms, ranging from fish to salamanders to crayfish. HVA has been very active, as you heard, in doing assessments of road stream crossings, bridges, and culverts to try to determine where you have passable structures and where you have impassable structures. And so here's a map that shows the structures that have been assessed largely by HVA and its partners. Also use modeling, and this is some of the work that we do with the data that's collected by HVA and others, is that we use it to model aquatic connectivity so that we can determine which of these culverts is the most important ones to replace in order to reconnect our aquatic habitats. And this is an example of a version of our critical linkages analysis that focuses specifically on cold water streams, and so that we can better implement that strategy of adaptation for cold water systems. With more severe storms, we expect more failures, and we expect more erosion. We expect more scour. We expect more things like superstorms, Tropical Storm Irene. We also expect droughts. And so we need to figure out a strategy for trying to minimize the impact of these flooding events and these drought events. The flooding events are certainly damaging to human property and infrastructure, but they also scour these streams and damage them ecologically. This is a stream in Vermont that was scoured by Irene. So we really need to try to deal with these floodwaters, even in relatively unpopulated areas. So that's a concept that we call slow the flow. Trying to store more water in upper watersheds so that we can reduce the impact of flooding and we can reduce the impact of drought through more base flow. How do we do that? Well, we try to restore natural channels and their complexity, their sinuosity. We accommodate beavers, which are able to actually back water up and slow it down and allow more infiltration in the upper parts of the watershed. Remove impervious surfaces in our more urban areas and our more developed areas. Reconnect our streams and rivers to their floodplains. create wetlands, are natural sponges which can hold water and allow it to infiltrate. And in more urban and developed areas, use rain gardens and stormwater management techniques, which can be considered like mini wetlands. Woody debris in the streams also help hold the water back. And this is an example of Trout Unlimited using woody debris purposefully planted in these streams in order to mimic the debris that's no longer there. And so here you can see those logs during a drought period, and you can see them later on when the flow comes back. And then finally, our forests are an incredibly valuable resource, and we need to continue to work to conserve as much of that forest habitat as possible and connect it so that species can move, their distributions can shift. If you look at North America and you look at the distribution of forests across our continent, it's often shocking to see how little forest there is in our country and how important New England is in terms of providing forested habitat for this entire continent. And so the Follow the Forest initiative that you have at HVA is an excellent example of strategizing to protect the most important forests and connect them together so that it can collectively support species at a level that makes those populations viable over time. And so just to wrap up, if you're interested in learning more about the projections for climate change in Massachusetts, I recommend Resilient MA. This is resilientma.org is a state website with a lot of data that was generated by UMass. And then another one is the climateactiontool.org, which is a website and a web viewing tool that I had a hand in creating that has lots of information about climate change, about projections for future vulnerability assessments for wildlife and ecosystems, and lots of examples of things that people can do to enhance the chance of survival for ours and health for our ecosystems and species. And with that, I'll stop. I know that I probably ran on too long, but I'll happy to stick around if people want to ask questions, and I thank you for your attention.
That was fascinating. That was great. Are there any questions? Any comments?
Put me on.
Definitely,
I want the
definitely a
vision.
lot of
I
applause.
want put my face up there.
Huh.
The face. Where are they?
I hear Elaine.
Any questions? Elaine?
I don't have a question, but I am so impressed with HVA sitting on the cusp of things that you talk about. And I'm thinking about so many things that Tim Abbott and the pictures that you show, they're touching on all of these areas. And I think we need a lot of help. We need a lot of funding. We need a lot of public support. There's so much to be done. It can feel overwhelming. But HVA needs, they need us, and they need the federal government and the state to understand more. We can't do it all at once, but we have an organization here that is sitting on the key points that you have raised. And you are so clear, Scott. Your visuals are great. We need to bring more to bear on this. Thank you.
Yes, I agree. And I think HVA is exemplary in its strategic thinking and its preparation. And that some of the work that's been done in terms of assessment and modeling and priority setting, hopefully you'll be well positioned for infrastructure money and other funding that's going to come down, and that you'll really be able to pick up the pace and do some of the things that you're planning on in the near future. And I agree with you wholeheartedly, Elaine.
Thank you.
Are there any areas where you think HVA could participate more than they are right now?
I can't say that I'm in a position to answer that question because I don't know all that you do. And so I could say something and I'd be thoroughly embarrassed to find out that you're already right on top of it. So nothing stands out for me at the moment.
Great.
I'd like to, for the water team to have a conversation with you about identifying those cold water refugia. Because I know we started to talk about that a couple years ago and, we're doing some temperature logging, but to actually identify those key areas sounds like it's pretty critical.
Yeah, I would agree. And that's really our next step because we've got a massive undertaking if we look at every stream equally. And Scott, is that something that we could work with you on to narrow the places that we really should be focusing in the next 10 years?
Yes, quite possibly. I'm part of a group of people that are waiting to hear on a grant proposal that we submitted. USGS is the primary applicant, and it's to essentially, create an approach for identifying cold water refugia. Ben Letcher has done a lot of work sort of collecting data on stream temperature and using it to try to model the temperature in streams that are not being monitored. But one of the critical issues is trying to account for groundwater inputs and water flow. And so we're working with a couple of scientists that have developed a technique for using fixed cameras to take pictures of small streams and crowdsourcing to look at those and compare images from those cameras in a way that allows you to actually generate information about the flow characteristics of the stream. And so when we can combine the temperature data and the temperature models with better flow information in these headwater tributaries, we'll be in a much better shape to identify cold water refugia. And if we get this grant, we're also going to be looking for partners that are willing to put out cameras and collect this visual data as we develop these tools a little further.
And that would be so timely because we're just starting in Connecticut to talk about groundwater, recharge and how to deal with development in places, and we don't even know where they are, where overdevelopment is going to affect groundwater levels. And it's such an unregulated area in Connecticut and in Massachusetts that this would be incredibly timely, and I'm sure HVA would want to participate, and I know we have a number of partners that would as well.
That would be great. That would be great. I'm going to have